tools for scattering. Remember that our interest is the binary, right? So we're interested in this problem and the emission of gravitational waves. And we concluded that we can compute, for example, a phase by using these tools in which we separate all the scales and we solve for the binding energy and we solve for the fluxes and so on. So now you might ask, well, how is this problem related to this problem? In which we send something in and we have an observable, for example. I'll tell you a little bit also about the radiative part, but for the most part, I'm going to concentrate here. For example, we get some binding energy. And here we get, for example, an angle. This binding energy is like some Hamiltonian. From that Hamiltonian, I can compute observables, mostly conservative observable. For example, the periastrum advance, how this orbits the rosette thingy that doesn't close. I'm very bad at drawing. So this periastrum advance, that can be obtained from the Hamiltonian. For example, as you might know, the first 1 p.m. correction, that gives you the 1 over r squared, that gives you the first periastrum advance correction. Oh, how do you materialize? You didn't come through here, right? Ah, that is impressive because I didn't even hear the door. You were hiding down there all the time. So that's an observable that we can compute in our theory. We can compute a binding energy, obviously, but we can compute a periastrum advance, which is an angle. Here we do scattering, we get a scattering angle. And you might ask, well, how does this have anything to do with this? Or how does this problem have anything to do with this problem? And the first thing that one can do, and this is the approach that was originated by the scattering amplitude people, is, well, if I can obtain from this problem an angle, and then I match this angle into some Hamiltonian that, let's say, works for hyperbolic orbits, whereas this works for elliptic orbits, as long as this Hamiltonian is local in time, then this guy and this guy are the same, so I can apply now this guy to this problem. And this is what people do. The problem is that it started at some point, this Hamiltonian will not be local in time, neither is this. And therefore, the calculation of the Hamiltonian itself depends on the trajectory, and this trajectory is obviously different than this trajectory. But if you have a way to understand and isolate those pieces, then there's a strategy. A good strategy means we get at least the local part of this Hamiltonian, and that local part of the Hamiltonian will map into each other. What I'm going to show you, mostly towards the end, is that here you can do this, but you can also map directly this guy to this guy. In particular, all the observables of these problems can be mapped into observable of those problems as long as we have local in time interactions. So all the local in time interactions are universal, and that can be mapped into one another. So if I solve this problem, I automatically solve this problem. And this problem turns out to be much easier than this problem for several reasons. Reason number one, I don't have to think. And thinking is good, but it's also nice when I don't have to think too much about the complications of gauges, coordinates, and so on that I have to do over here. Here, I send something in, I collect something out. Whatever happens in the middle, I don't care. So I have some incoming state, and I have some outgoing state. And this is P1, and this will be P2 final, and this will be P2 initial, and this is P1 final. So these guys come zoop. They have a distance of closest approach. They have a scattering angle, and I'm mostly, remember, in the conservative part. Of course, they will radiate as much as this problem. And you might ask, well, how does the waveform of this problem relate to the waveform of this problem? That's a little more subtle, but I can show you how to construct all the ingredients of this problem from this problem, at least to very high orders in the post-Newtonian expansion. Which means that even also if I solve this problem with this radiation in it, I can also map that to this problem. And then we're in business, because if I can solve this problem, then I get solutions for this problem, but I get extra things. And the extra things are like this problem will be an expansion, if this is our impact parameter. This problem will be an expansion in the weak field, like GM over B is going to be small, or if you want, the angle is going to be small. But I don't say anything about the velocities. The velocities could be large. And while this problem allows us to use the fact that a bound state has a relation of scales, and power count G's with V's, and go to very high orders than V's, and also going higher than G, this is the post-Newtonian expansion. And remember that in the post-Newtonian expansion, we split our integrals, so we get all that quasi non-instantaneous part of the force expanded, so we get static integrals. And then when we do the matching, we also match into a theory of potentials, where all these interactions are quasi-instantaneous. So we only see the on-shell modes in the far zone when we start seeing these tails that I didn't tell you much about, but I'll comment here on how they appear there. But for the most part, the PN expansion allows to solve the integration problem one scale at a time, and that simplifies your life. This one here, on the other hand, is the so-called post-Minkowskian expansion. PM for sure. PM, it's a little bit annoying, obviously, but those are historical. Here, I don't have to assume that I have small velocities, and therefore, all I do is expand in G. What does that mean? That means that if I tell you that I have now some accuracy up to 5 post-Newtonian order, the state of the art, at least in the conservative part, the part that has to do with Hamiltonians and bindings, then I go to V to the 10. And if I go into V to the 10, beyond the Newtonian, when the Newtonian is a G, so the G squared would be 1 Pn. So I go 5 times more, I get G6. Because I go 5 post-Newtonian orders, so V0 is the leading order, but the leading order, remember, is the leading order interaction, which is V squared minus Gm over R. So clearly that's the 0 order scales with V squared, or it scales with G, so you go 1 Pn is G squared, and so on, right? So that's why you have to go to very high order in G, which is really hard from this point of view. But we don't need the whole G6, because we just get the static part, and that's easy to calculate. In fact, you can even calculate that piece first, if you want. Which indeed, I think it was done originally, the static part first, also by Bloomland and company. This was done partially. So this full Hamiltonian, at least part of the Hamiltonian, not all the hereditary effects, but was done by the whole thing, I mean, the whole Fabian. The static part was done by Fofa et al. And the next day by Bloomland et al. But But you see, you can separate the calculation, which is very nice in post-Newtonian. Here you get it all at once. There is no static, at least in the solution. So this is fun, because it's nice that we get at G to some order all the corrections. So if I can then map this problem, the Pn problem, into the Pn problem, then I don't complete the Pn order, because at any Pn order, V and G scale the same way. So obviously, I'm going to mix powers of G. When I go to a given Pn order, as I was doing in the colloquium, we had this list, they mixed up. You get G6, then G5 V squared, then G4 V4, and so on. So I get half. This gives me half. But at the same time, it includes all the velocity corrections of the next orders, of the next Pn orders. So it's true it's half only, but then you get extra stuff from the fact that you get all this tower of velocities. And that means that if you were to construct a Hamiltonian, say, and then you get some p squares in your Hamiltonian, then you're going to get a G to some power in your Pm expansion, then p squared, p4, blah, blah, blah. All of that resum into some function of p squared, which will be some complicated function. This is if you expand it. That doesn't mean that you're going to get a polynomial. And in fact, this is going to be the fun part. Here you don't get necessarily polynomials of the velocity. You get some functions of the velocity, which when you expand, you get all these terms. But the resum version of this thing is a relativistic, special relativistic invariant function that will give you the whole information of the scattering. And what is that invariant? Well, that invariant has to do with the fact that there's an initial velocity or momentum, m1u1, there's an m2u2. So what is the relativistic invariant here? The relativistic invariant is gamma or sigma, depending on who you talk to. And we use the mostly minus signature, so this is bigger than 1. This is eta mu nu with 1 minus 1 blah, blah, blah. Which is related to the relative velocity of the system from the point of view of the center of mass. You can, for example, look at the momentum. Let me write that over there. Otherwise, I'll write the variables here. But this is the main lesson. The main lesson is that obviously the angle will be invariant under boost, and therefore it's going to be a function of gamma only. It has no other thing to depend on, right? And of course, an expansion in Gm over B, because obviously there is an impact parameter, but this is dimension full, and the other dimension's full scale is Gm. So that means that our angle, which is going to be, our goal is going to be to compute this angle. And once we map the angle into observable, so once we get that angle from a Hamiltonian, you'll see that this function of gamma will give us precisely this resummation that we have here. It will be a function of gamma. And we're going to write it as a sum of some order in the PM expansion. So we will need these coefficients. And that's our goal. Our goal will be to compute this in an expansion in G, in which we do also, like in PN, a weak field expansion, but that's the only thing we're going to assume. We're going to assume that there's a small perturbation, there's a weak field perturbation, that was going to give us the expansion in G. But we are not going to play anymore with our Green's functions and say that the bodies, the sources are moving slowly, like we do in post-Newtonian. They can move as fast as they want. Now, that's not, let me just say one thing. That you have to take that with a caveat, yes and no, right? Because you cannot take more energy out of that you put in, right? So you have to be careful also with what you mean by going to gamma infinity, for example. Say if you compute that radiated energy, and then you start radiating, and that radiated energy grows with gamma, then at some point you have a cutoff that you just don't have enough energy to radiate. So then you have to be careful with that. But at least for the conservative part, we don't have to worry. Yes? The what? We are not capturing here, right? We are in an approximation which is a small angles. That's the post-Minkowskian approximation, that this is a small perturbative expansion. This does not capture. You can do something to describe capture, which I'll try to maybe describe later, which is say you map this angle into some Hamiltonian, say, for example, or something that I like to call the impetus formula, which is the inverse of the Hamiltonian. The Hamiltonian determines the energy, right? So it's a function of momentum, and usually we map into what is called the isotropic gauge, that we can map this into a function which is only a function of p squared without spin. If you have spin, obviously it's different, but if you have spin, if you don't have spin, you can match into the isotropic gauge. This is obviously gauge dependent. You have to ask me which gauge you're going to choose to define this Hamiltonian, what does it mean, the gauge, and so on. That's another question. That's why I don't like the Hamiltonian. But in any case, just to tell you what you can do, this is E, the energy. But if you invert this as a function of p squared r and E will come from gamma, because gamma knows obviously about the binding energy of the system, then instead of writing this, you can write the p squared as a function of gamma and r. And now this p squared, you can say, I know it up to some G Newton order, and I'm going to decree that that's the true theory, and I'm going to compute the angle now with that p squared. And that angle now doesn't truncate anymore, the same way that Newton doesn't truncate, right? If you put a p squared, if you put a Hamiltonian of 1 over r, so if you put the first p squared 1 over r correction, the angle has all contributions. So this chi, in fact, Newton gives you a lot of corrections. So that's kind of like a bit of a circle, right? So what is the p squared? What is the Hamiltonian that give me this angle up to here? That means that I control the Hamiltonian up to that order, and then I can say, what is the whole angle that I get from it? And you can try to then push to higher impact parameters by doing that resummation.
Right.
And that's something that has been done and actually works really well, surprisingly. We did this through the mapping of p squared and the angle, something that I like to call the fields of representation or the fields of resummation, and you'll see maybe how that works. But that's as far as you can go. The perturbative expansion breaks down if I try to go to low impact parameters. Right? Very good. And so where are the kinematic variables? So we have an initial, so that was the description. Let me just be more specific now. So I have a U1, a U2, I have a V, and I have gamma. That's the guy that I just defined for you, that everything must depend on. But if you want, this is P1, P2 divided by 1 and 2, right? So that would be like the Mandelstam parameters, right? So this is large impact parameter scattering. This is not an S channel, it's more like a T channel, right? And then we have a bunch of variables. So first, the usual ones. So we're going to have expansions also, which is useful. It's useful to introduce the mass scaling as well, because in the angle there will be a very interesting thing happening from the mass scaling of the angle, and how that we can try to map that mass scaling of the angle into the Hamiltonian or the observables of the bound case through this correspondence that I'm going to tell you about. So this is the same by m squared. So again, because this is symmetric under exchange of 1 and 2, then this nu is going to come up in the solution, and this nu knows to what extent you're departuring from the test body limit. If I scatter in Schwarzschild, I'm not going to see any effect from the small body, call it 1, right? And a lot of that information in the angle is just Schwarzschild, right? Then there is some called the first self-force correction, where you start getting the factors of nu that you don't get from Schwarzschild, but we're going to get them here in post-Minkowskian. But the cool thing is that there's another expansion, which is post-Newtonian goes up to some order in B and some number in G. Post-Minkowskian goes up to some number in G and all of the velocity. And then the self-force expansion truncates nu, but gives me all the G's and V's. So there are many directions in which we can attack the problem, and that's why now, especially from the point of view of scattering, this mass scaling is going to be relevant. And that's why now I make it explicit. Then obviously there is the energies. So we have the energies of each particle. So the momentum of each particle, right, is P1 is equal to M1 P1. If you go to the center of mass, then this is the P mu. But the momentum of the particle 1 is equal to the momentum of the particle 2, and it's equal to P. Sometimes the incoming momentum, the relative incoming momentum is called P infinity. So equal to P infinity. And therefore the energy there, it becomes just these factors. This P obviously knows about gamma when you go to the center of mass frame, so you can just calculate gamma in that frame, do the contractions, and then that's the relation. The relation turns out to be like this. So this P infinity becomes mu over big gamma, which I'll tell you in a second, square minus 1. Where this big gamma is the total E divided by the total M, with E is E1 plus E2. And M is M1 plus E2. And this is the key. The key new feature, this is like the velocities until this is called V infinity. That's the relation. This is the key feature that distinguishes a two-body system from a one-body system. So a lot of what I'm doing in the center of mass look like a one-body thing, the same way that the Newtonian problem does, right? There is some relative momentum, which is the same for both. And there is like a total energy of the system, E. And what is the difference between the test body and the two-body case? It's this guy, essentially. Because if you're in the limit in which one of the guys is immensely heavy, then you're basically dominated by your background. All the contributions from the energy that know about the other guy, you don't see. But because of the way that the relativistic invariance works, this is the guy that will carry all that information once we put this back into the solution. By setting this equal to 1, we get the test body, and then we see how these masses are going to enter through this factor of gamma. And that's going to be part of the catch of how we get a lot of this mass dependence. This I define. Yes?
You only say
Sigma?
sigma.
Did I say the right sigma somewhere? this big gamma, E over M, mu, gamma, where is sigma, V? M? Huh? This gamma. Ah, that was a sigma. Sorry, gamma. Gamma. Ah, good one. Also, sometimes in the literature of the amplitude people, they call this sigma. I don't know why. Because, well, I do, but this is traditionally what the GR people have used. Yes, sorry, gamma. This is nothing but solving these equations, right? It's no mystery, right? Yes. What was I saying? Blah, blah, blah. Yeah, so in this approximation, obviously, gamma has to be bigger than 1. So this is unbound. And that's going to be part of the whole story. We're going to analytically continue to the bound case by going gamma minus 1. And that will be part of our dictionary that will take us from this problem to this problem. We'll see how that goes. But for now, we are in this regime. Obviously, gamma is bigger than 1. The energy of the particles at infinity is positive. You're free. You're free to go. If gamma is negative, this does not exist. You just cannot live, right? You're bound. And that makes a bit of a difference, but since it's, okay, I don't want to get ahead of myself. Since you can go from one to the other, we'll see how we do that. So, very good. I wanted to define one other thing that is going to be useful. So there is something, sometimes, I don't remember how other people call it. I think we always call it epsilon, which is the binding energy. Over M over mu, sorry, the other way around. And that's good because this is what determines if you're bound or not, right? If energy is bigger than M or less than M. And this divided by mu is just for the scale. That's all. And then the connection between this gamma is very clear because then you have that is bigger than 1 if you have positive binding energy or less than 1, but there are nulls here as well. And that's also another feature which is important. There are two important features here. If I then write an answer that knows about this guy, then all the mass dependence is here. But if gamma now is a Pn expanded parameter because it's the powers of, like, say, the binding energy, because you're going to calculate an observable as a function of the energy of the system, like a periastrum advance, for example, that you can Pn expand, there will be factors of nu hidden inside gamma as well. So what relativistic invariance is doing for us is encapsulating the form of these functions that have to enter in this way in the solution. And if I know then how to map this to bound, I'm going to inherit all that structure into the bound case, which originally was very hard to see where does it come from. But the fact that one can map one into the other basically inherits that structure. You see there is something here, right? There's an asymptotic symmetry of asymptotic Minkowski that you don't see here, but it's carrying a lot of information because this local interaction basically is the same for both. So whatever constructed this solution that we know is relativistic invariance in the full solution in which you resum this shit, right? Then that information is to be carried universally to the bound case. Not always. The freaking tails spoil all of this, but without the tails, this will be beautiful. There's an extended symmetry here that basically in the PM expansion allows you to really understand all the structure of this problem. What do you mean? Tails. What is the tail? Yes. This radiation will talk to the mass monopole of the binding. So remember in my theory, I had some emission from the quadrupole, but I also have the binary talking to that emission. These things are called tails. And those things also contribute to the angle, obviously, to the deflection, because it's like a radiation reaction force that is corrected by the tail, And that is not local in time and changes these things. We recently learned a little bit more how to deal with those, but that's a little tricky. This is beyond these lectures, but I will briefly mention this just to show you how it works. Okay, so this is very nice because the kinematics is already telling us a lot. Without doing any work, we already start identifying the relevant parameters of my problem. We already know what this has to depend on. And then what are we going to calculate is an impulse. What is the impulse? What is the change of momentum? So there will be a final guide. There will be initial plus impulse equal final, right? So there will be a change in the momentum. Why that is useful is because if I know the momentum, I know the change of momentum, then obviously I know the angle. You can do this as an exercise. This is just going here. How do you define the angle? If you go here, it's a chi/2. And then you get this, this relation that this is equal to, in our signature, because it's a space-time, that's the minus, because I want the space-like part, divided by the magnitude, which is at infinity is p infinity. And this is just, I mean, there are other ways to do this. That for historical reasons, we did it this way. But what I mean here is that you have a chi, and then you have a chi3, and a dot. This is minus a third, I think. So you need to span this guy. So when you try to solve, you have to be careful that if you want to sum, for example, the third order, the 1 will also contribute. You have to put it on the other side. If you compute this to third post-Minkowskian order, there is this guy that pollutes the answer of the chi3 because you have to span the sign. But that's trivial, right? You see what I mean, right? So what this means is that if I know delta P to a given PM order, then I get the angle to a given PM order, and this is what we want. This is our guy. Yes? Yeah, so what I say originally is that I'm going to do conservative. So if I do conservative and no spin, then these are all even. The moment you add dissipation, which I haven't, I'm not going to talk much about, I don't have time. When you have the radiation, you can also map the radiation. You can also do things with radiation. It's a little bit more, it's a little trickier. Then you can have odd in velocity terms. Yes. But here we're going to have even in velocity. That doesn't mean, actually, I should say, that doesn't mean that I don't include the radiation. I do include the radiation, but I'm going to do only conservative radiation, which I'll tell you what it means. But I'm not allowing myself to lose energy to infinity. So we want to compute delta P. So we do the same thing that we did in post-Newtonian, exactly the same. We have an action. So we have a bulk action. We have a total action, right? So we have GR. We're going to have the point particle action, which I'll tell you in a second what it is. We have sum over the particles. These are my sources. Like if you're doing field theory. There's some gauge fixing, which I'm not going to say much about, but you can play with. In fact, it's very convenient to play with the gauge fixing terms to simplify your life. And we compute the same way that we computed before. So we have some effective action of the sources that come from integrating all the gravitational degrees of freedom schematically. So, and here, this guy, we use vacuum in, vacuum out in the presence of the sources, so no outgoing radiation. This is a trick, because in reality, what I want to do is solve the classical equations. That means that it's not vacuum in and vacuum out, it's only vacuum in. So the correct way to do this will be doing the so-called in-in formalism, in which you solve the field equations with the correct retarded boundary conditions. But this will take me a little while just to even introduce how this in-in works. This is a subset of this, in which I cannot symmetrize this retarded propagator to get a symmetric propagator, to get a time symmetric part of this calculation, which is this calculation with Feynman boundary conditions. And that's because this calculation, when you do the closed term path, for those of you who know, you come back. So you actually do have a piece which is Feynman, Dyson, and then there is a piece which is the cat, which the Feynman plus cat gives you the retarded propagator. So this part is essentially ignore the cat part and just do the Feynman piece, which is the time symmetric piece of that calculation. And that will give me a conservative part, which will also correspond, at least to the level that we have computed, we get in the time symmetric part of the propagator, or the so-called principal value, which is also the one that people in the more traditional approaches use. If I have time, I'll show you how that much works. But what this means, that means if I use Feynman propagators, and if you have any familiarity with in, then you do get the Freeman and Dyson piece, and the Dyson is a complex conjugate. So actually, to get the part that you want, there are two components. So there is a real and imaginary part. So here I have to compute with Feynman, but keep only the real part, because it's essentially you get a combination like this in the answer. Sorry? Somebody screaming? Don't murder anybody, please. So this is a lot of fancy words to say I do the retarded boundary conditions in my field propagators. Then I rewrite that retarded propagator as a Feynman plus a cat, and I can show that the Feynman piece essentially captures a conservative part of the answer as long as I keep the real part. And this coincides with the time symmetric propagator that also is the Wheeler-Feynman propagator. All of that fancy words just to say that I'm going to compute here the conservative piece by just using the standard calculation that we all love. And the same way that I said this serves as an action, this will give us the momentum, because then the P dot will be, and this is just a choice of signature, from the interacting part, which is the part that I want. The momentum only changes through interactions, right? I mean, that's because the definition momentum will be the LDV that will go into the kinetic part to give me the P, and then the whole P dot will come from the action. I mean, there is no X dependence in the zero guy, which is just V squared, as we'll see. So all the dots, all the dynamics will come from the interaction. And if we integrate this in time, then we get the change in momentum that will give us the integral of precisely this guy. And this I get from here. And then I get my momentum. particle A. I need to be more careful with this in retarded story, but I'm not going to get into. Now, what is this? It has two pieces, because then we have dl dx and d by dt dl dv. But this will be a total derivative, and as long as the interaction part dies at infinity, I can ignore this, and I can just compute with this. So then I just integrate this part here and drop this. This is okay as long as the interaction dies at infinity. And actually, this is true so far. You might have to be careful from 5 p.m. on because of memory effects. But let's not get into that. The interaction dies out. This is all we need. So it's the integral of this thing. But this is evaluated on the trajectory. So I need to do this iteratively. To a given PM order, I'm going to get the first iteration by assuming that there is no deflection, then the second iteration by assuming that there is a deflection at 1 p.m. and so on. So I'm going to solve these equations iteratively. I'm going to say that the motion of the particle is going to be some impact parameter, the Ampere-Torr solution, some velocity at infinity, and then a bunch of deflections. And the same for the velocity. And notice that V and U are not the same. This U is the velocity at infinity. And because the interaction is going to turn off at infinity like I have assumed, then I get not only this, I also have that these guys are 1. It's Minkowski space at infinity, which means that this V is unit in G mu nu, but it's not unit in eta mu nu. So GVV is 1, but eta VV is not 1. Eta UU is 1, but GUU is not 1. And that's important, okay? And this means that I have to evaluate this guy here. But because the interaction will cost me G, so when I do this calculation, this guy is going to come out when I integrate the metric at orders in G. So there will be an interacting term at order N. And that means that if I want the first N 1 p.m. angle, I don't need to plug here the interaction because that would cost me another G. And I don't want that. Then I can just treat this as an Ampere-Torr trajectory. So what I do is that I need the N order or the N loop order interaction on the given order deflection up to what I need to the given PM order. We can do all of that diagrammatically, and that's how I'm going to show you in a second. And once I have, and where do I get these deflections from? It's by solving these equations, right? And these equations are up to t, and this is going to be important. I need to integrate this equation up to time t to compute who these deflections are. And I'll show you that in a minute. And then just crank. Is that clear, more or less? Yeah? how do we crank? How do we map this? Notice that it's slightly different than the whole post-Newtonian story. I'm going to show you essentially a very systematic way to compute this. Because there are no coordinates. There's nothing left. Here, you're going to end up with some function of gamma in an expansion of Gm over B, done. So all I have to do is an integral. That's it. The integrals are hard, but that's all I have to do. So I haven't told you who this point particle part is. Now, remember that in Pn, we wrote this and then we wrote this with the reparametrization invariant form with some affine parameter. And then we say, this is very useful in post-Newtonian because we want to compute waves that evolve in frequency. That frequency is associated with a time in my detector that can synchronize with the time, the Schwarzschild time like we do with black holes. That is the one on the center of mass of the binary. We're looking at that time. I mean, there is, they think it's moving, maybe there's some recoil and so on, but those are small effects. And we start measuring when we get the wave there anyway. And that's very convenient because we track the time. We track the frequency. That's not what I'm doing now. Now, the parameter, the time parameter, is being truly integrated between minus and plus infinity. I'm following the entire trajectory. So this action, which is completely fine, has one nagging problem, which is not only these centers, also all of these guys. Because I expand the square root, I get h squared, h cubed, blah, blah, blah. We don't want this, because why complicate your life? So in our first paper, and I think we were the first to do this as well, then other people adopted this, we choose another action, which is a so-called, well, I think Thibault will complain it's not the Polyakov action, but because the string theorists use it for the Nambu-Goto string and the point particle, which is not a two-dimensional, but 0 plus 1. So the one action is a sum of the two, but what we have here is G mu nu, B mu, V nu, divided by 2. And this, I'm not going to call it Polyakov, but it's the linearized, which means I want to get rid of the square root. I introduce a Firbein, and then I set that Firman to 1 by choosing the proper time. It's the same with the surface when you have a string. And this has the advantage, just 1 point. 1 point. So it contributes only to this 1 point function. And that's very nice, because that literally simplifies my life. Now that's tau, right? That's the program, but who cares? It's being integrated. That does mean that when I get this has the proper time at infinity, which is okay, because that's the gamma that I want. So what does that mean now? That then my action, my point particle action, which I'm going to use, just gives me very simple Feynman rules. And then the bulk, which I have over here, so this will be this part. The source coupling will be very simple. Now, this guy, this is the gauge fixing part, but this, what is this giving me? This is giving me the propagator. So let me erase the gauge fixing for now, which is there. This gives me the propagator that I need to invert. And then it gives me all the rules. So the action gives me, without the source, it gives me the propagator, which we have this form with some tensor structure. That will be my propagator. And these guys will be like cubic, quartic, and so on. So the bulk gives me these rules. The source gives me just this. We're good. We almost have everything we need. So to construct our effective theory, our effective action, sorry. This is too big. Let me just rewrite this here. Do I have to say anything here? No, I think I have everything. So then I have linear terms from here, and then the bulk action, Einstein-Hilbert, gives me the propagator plus all the endpoint functions. And then I put that together, and I get my effective action as a function of the sources, and the sources are these particles moving, this x of time, x of tau, which is what I want. Now this is the exponential. This is what, if you do field theory, this is the W versus the C. So this is the connected diagrams, the 1PIs that I need. So no disconnected diagrams. Also not closed loops, because I'm not doing quantum mechanics. So I have sources, as many as I need. They don't propagate, right? They are external sources, and we'll see what that means. And I need to hook them together, but I don't want to close any loops. Certainly, I don't want this, because no running. That's not needed. But also no corrections like for example, if you have things like this, like vertex corrections, because these things will scale with H-bar, and the only scale of the problem in this scattering, it has units of angular momentum, it's the angular momentum of the system, and this is very, very small. So no loops. So what does it mean? That means that, for example, I'm going to have, when I want to go to some PM order, where there will come in factors of G, the factors of G will come when I hook things together, because the way I did it, I ate away this G in here. So when I hook H's in my propagators, I get G's. And then the vertices will also come with them Planck upstairs, and that will make it all the G's that I need. So I start with the first guy, 1 PM. Then I need this guy. This is for my effective action. So my effective action is a function of J. It's this guy plus this guy plus this guy plus or in principle, I also have this guy. They could be higher endpoint functions. This one doesn't contribute at the end, but and so. There is also this guy. Always truncated with sources, right? That's for this part of the calculation. And we'll see, because my guys are localized on a word line that when I compute this, the source will be a delta function in momentum space. It will be an integral of an exponential between minus and plus infinity, so they will look like loops. These integrals will look like loops, but they are not loops. It's just iterated Green's functions on localized sources. That's this part. It's very similar to an IGR, right? It's exactly the same. It's just that in IGR I stop there because I get a potential. Here I don't stop there. I integrate that force. In IGR we stop. We say we have a force and that's our potential, and then we use it to compute things because it depends on the coordinates, blah, blah. Here I don't even look at it. I just put it here. That's very useful because then I don't have to think. And if I don't have to think, I don't make mistakes. Now, all of this, remember, now source, this is x. Now the problem is that x itself, the j's themselves are the trajectories. These j's themselves are the trajectories. And they carry also GN corrections. So that means here, when I do this, I need to go back to my deflections that I'm going to plug in here. These guys are the x's, so I'm going to have the Ampertov trajectory. So it will be this, we can call it x naught, which is Ampertov. So I have the x naught Ampertov plus all the deflections. And these guys carry G. So if I want the deflection up to G, I need this function, this functional, up to some order G, which will be all these diagrams. They will then depend on some unknown function. I cannot do this integral. This integral will be very hard. I'm not going to do that. I'm going to write this as x naught plus deflections. Now the x naught part I can do, and I show you how. This is easy. Why? Because e to the x, kx, replaced by u tau, or kb plus u tau. The kb goes out. That will give me the Fourier transform that is going to give me the 1 over b. And the k u tau, integrating tau, is going to give me a delta function. And that is an integral that I can do. The delta x part, I have no idea how to do. But since it's perturbative, I bring it down. And when it's down, I know how to do it. So I iteratively add those corrections. And then I want to show you how the 2 p.m. work. The 1 p.m. is trivial, I'll show you now. How the 2 p.m. work. You will see how the 2 p.m. works, and then you know how the whole thing works. So the catch here, the difference, is that I'm not adding a diagram for this. Why I'm not adding a diagram for that? Meaning I could quantize x. I could totally do that. I could add a propagator for x and integrate. And this is also what the group of Jan Plewka and collaborators do. It's a bit unnecessary because since I know the equations of motion, I basically get all the iterations from here. I don't have to, it's multiplying the work. Okay, not necessarily a lot, because if you know how to do these iterations, then you can just add them up, but it's much easier conceptually also to understand what is it that you're doing, which is just solving the classical equation. In NRGR, it's the same. We don't quantize the wall lengths. We sort of quantize the gravitational field, but not the wall lengths. Okay? So how this works, that's computationally, which is ultimately what we need to do. Let me show you then an example. Is it clear what I'm talking about? Yep, super. Notice that this is very clean. It's very clean to set up this problem like this. I don't have to basically tell you anything about GR calculations. There's almost no GR here. right? Because, or binding energies of gravitationally interacting systems. I'm looking at it's kind of like a scattering amplitude. In fact, this also maps, as maybe I'll show you, in an idea of literally computing an amplitude, right? From in and out states, right? So what is the 1 p.m. angle? How do I get the 1 p.m. angle? Well, first I need the 1 p.m. action. And the exact 1 p.m. action comes from here. So here I have the GVV coupling, 1 and 2. And here I have my full P propagator. And we're using the Feynman boundary condition, as I told you, even though up to, well, you'll see. The I0 doesn't matter. You'll see when the I0 starts to matter. I don't have to do anything. Even I was doing retarded here, the I0 wouldn't matter either. And that's because the first time you start seeing energy loss in this process, the scattering here, you only start seeing radiation at 3 p.m. So GQ. That's when you start seeing that the I0 matters. It's when this guy can go in shell, essentially. Now, notice that also, when I do the source, actually I have to be careful, because here's a little bit misleading. I purposely put the J's away from each other, right? It looks like this is J1 and J2, which is what I did there. But actually J is J1 plus J2. So technically speaking, I must also add this diagram. However, without the radiation, that is not going to matter at this order. The integral that comes from here doesn't have the impact parameter. And therefore, it will be an integral that is totally scaleless. So something very important is that dimensional regularization will set this type of integrals to 0. And the same happens in NRGR, by the way. The same happens in NRGR with potentials, but as we're going to see, this will be localized in a potential, and then it will be the same. So we get essentially P, V1, V1, V2, V2 contracted in 1 and 2, and M Planck square. I forgot, I think there's a factor of A. I think downstairs maybe. Yeah, downstairs. So this is the same calculation you will do. It's the same calculation you will do if you're computing a vacuum amplitude. This is literally vacuum, but the sources truncates the fields. So just to be pedantic, if you want. So there's this term that often sometimes you see when also known as the name of phi, like the phi scalar field. And then vacuum, but in the presence of the source is the interaction part. And then you bring this down, then you get JH, and then contracted with the propagator, HH. So that gives you the propagator, JJ, and that's what we're calculating, right? Good. You can literally do this yourself after a QFT course. So then we get the P square part. We get here x1 of tau minus x2 of tau and there is a D for P. Which, as I told you, I'm using dimreg. So here I can put the corrections. It's not relevant now, but later it will be important that we do this integers in dimensional regularization. And then there is a DT1, DT2 from the word lines. And I told you that I need the derivative with respect to x, and that's going to put the P mu here. Up to a sign. From the momentum. From here. Yeah, this is the momentum. Sorry, yes. No, the action will be this, but now I want to compute the momentum, which is the derivative. With respect to x1, say. It's the same opposite sign with the other guy, obviously. And that's the derivative with respect to x. And integrate in tau. So actually, I'm kind of cheating, right? I need to take respect to x, that fixes a different tau, but then I'm integrating that term and calling it the same way, right? So I'm kind of cheating a bit because I had to derive, the equation depends on some time t, but then I integrate in tau again. And that's why I get the other integral, right? So there it's going to be, later it's going to be slightly more complicated when I have to integrate up to some time t, the solution. Right now, when I do this, I integrate time t, so I lose one of the integrals, but then I integrate in time again, so I get it back. Right? And in this case, nothing happened. I didn't get anything other than this p. And now, I mean, the dp, it's just, there's no time, right? I'm integrating in time, right? But I need the solution. The point that I'm trying to make is that I'm not going to include any solution yet of the perturbation. Later, it will be important to distinguish. And then I just plug b plus u1 tau, x2, b plus u2 tau 2. So this is the exact 1 p.m. action on the undeflected trajectory. This will have, if I include all these delta x's now, 1, then it will be the exact 3-level exchange, the exact 3-level action, up to all post-Minkowskian orders. For example, if you were doing QED, that would be the end of the story. And therefore, this is the end of QED. If you add all these interactions here, you compute the full QED case. It's very hard, because the moment you start getting these iterations, as you will see, you get very complicated integrals. But if you could solve this theory, if you could solve this integral for a given trajectory that you can parameterize, you're done. Now, that's hard. I don't know how to solve this integral. I mean, I could do a self-force expansion of this integral, and people have looked at that. You can expand around the geodesic of a given Schwarzschild solution, say. And that you do new mass expansions around that, so that you can also try to. We're not doing any of that. We are just systematically including all the PM corrections. And what this means now, well, this is B1 and B2. So this gives me B1 minus B2, which will be our impact parameter. So from here, the velocities now are the dots of this. If I don't include the perturbation, now P does become U, and U does get U squared equal 1. here, I do get terms like V1, V1. With eta, that is not 1. Okay, this is important. But U1, U1 is 1. U1, U2 is gamma. So this will give you 2 gamma squared minus 1. Which you might already... Yeah, exactly. But this P is eta eta plus eta eta minus eta eta. So obviously V does not contract with eta well, U does. But because I'm a leading order, that's okay. When I go to higher order, I perturb this. I cannot use VV eta 1, but I need to include all those corrections. And that's important. G VV will be 1, but I'm not perturbing G, meaning I'm not using any background. I don't have the full G either, so I could not do that. That would be also kind of circular. So, but U is 1 and gamma is gamma, U1, U2 from the cross terms. So this is the overall coefficient. So then I get the 2 gamma squared minus 1. Which is good. I get what I always get. This feature will always be there. There is a P dot V. I call it P now, but often it's going to be like a transfer momentum. So I just change Q and P just for the fact that Q is usually associated with T like minus Q squared, like the transfer momentum. Then the integrals of K dot U tau will give me the delta functions of U1 and U2. And these guys are always there. They always come out. There will be more integrals, but the last Fourier transform will always be an integral like this. And there is the P mu, but from integrating tau. K or P or Q times U tau. And I'm going to, there was a P, and so actually I should have, so there was an I, but there was an I, and then what I'm going to do is trade that by dV. So I just need to take the derivative of this, and this, guys, if I go to the frame, in which is the frame in which particle 1 is at rest, and this beta is the velocity, if I'm not mistaken. And this is more. Yeah. So then it's very easy, because essentially you just put this into the orthogonal plane. You do pick some factors from the conversion, and maybe do this as an exercise. The only thing you need to do at the end actually something that I haven't used, but it's also obvious, is that the U is orthogonal to V, even though I'm using a V as a V mu. So here I'm using a V mu. It's really orthogonal to U. So then at the end, what I need is just this general integral that is, do I have the answer here? Yeah, with some d-dimensional integral and any power. This is e to the minus I kx. This is if I did this correctly, this is 2n, then pi d over 2, then gamma d over 2 minus n divided by gamma n, and then x squared to minus d over 2 plus n. And all you need to know then is that it's two-dimensional. So then we need this guy in the d equal 2, which actually is a little tricky because it gives you a log and a pole, but the pole, when you take the derivative, goes away, and the derivative of the log will give you the 1 over b. And you end up then with the answer and then for the angle, all you need to do is very easy, because once you have the delta p, which is in the b direction, all you need to do is the absolute value of the coefficient divided by p infinity. So at the end of the day, after you do the absolute value of delta p, there's no need to so delta p you can parameterize in components. There will be delta p. We have something in b mu, something in u1, and something in u2. And this one will matter later. At 1 p.m. we just care about this. And that means that at higher orders you do care about this. But because delta p of p squared is m squared, which means p plus delta p squared is m squared, and this starts with u, that you can get the u component from the b component, because delta p u will be delta p squared, and it will start in the next order. So you can always get the u components of the conservative part, in which also the delta p, so delta p1 plus delta p2 is 0. By getting the b direction. So the b direction will be enough for us to get the component, because then you just get the other one for free because they are conservative. Now the point is you want an angle, so you get the absolute value of the delta p. You divide by p infinity, and then you get sine of chi. But at leading order, sine of chi is chi. So you get this chi over 2. So getting this coefficient at 1 p.m., these guys are going to start with 2 p.m. So they're not there. This coefficient, divide by p infinity. The coefficient you get by putting that integral gives you a log. You take the derivative with respect to b, you get 1 over b. So the only thing it was the measure. And the measure you get through these coefficients. And then you get the chi b1 becomes 2, gamma squared minus 1. And remember, they had to divide by p infinity, and that was the gamma. That appears upstairs because it's downstairs in p infinity. So we put it now divided in chi. And this goes gamma squared minus 1. I'm just, otherwise I don't have time to go a little more detail, but this is not complicated. You see how this goes. Yeah, then the other things have to do with the measure because of the q when you do the integral. And then basically that takes care of all the factors. Yeah. What was I saying? Yes, the gamma. No, so now what happens? Notice that this does not depend, no dependence. Only m, total m. the angle came out with M1 plus M2. Huh? Yeah, exactly. So there's a G, here there will be a G. And the delta P has the mu, and the mu M will give you M1 and 2. So when you divide by P infinity, you pick up the mu of this factor and you get the M. So the angle depends on M1 and M2. So the angle at 1 p.m. it has just this very nice gamma squared minus 1 chi over 2 gamma. No other than the total mass. Total mass. So where are the nus? They're all in here. That's the only thing that distinguishes. The answer in Schwarzschild is identical. This is Schwarzschild. The only thing that distinguishes this from Schwarzschild is who is gamma. Gamma in Schwarzschild will be this guy for Schwarzschild, but this is sitting at rest. So it's the energy of the other particle. But I can just identify it with gamma. If I look at the answer in Schwarzschild and I see the energy of the particle, that's my gamma. And that's the answer. With the energy of the particle, that would be the U1, U2 Schwarzschild, which is just sitting there. So if I identify now this energy with the gamma and the M with the mass of the total system, not with the mass of Schwarzschild, but the mass of the total system, because the other one is misleading, is subleading, then I get this part for free. All I need to do, gamma, the energy is gamma, and the mass Schwarzschild is the sum of the two masses. What am I missing? I'm missing this guy only. But that's the structure that we just determined. I know that it comes down here. I know that it came from the only difference between the P infinity in a test body and a two body is this guy. Therefore, I can predict from Schwarzschild, just by dividing by gamma, which is the total energy, I can predict that this, essentially that the two body case will be chi Schwarzschild, exactly the same, multiplied by gamma. Here with the identification of Schwarzschild to M1 plus M2 and energy of the particle, I should call it differently because I call the binding energy E of the particle with gamma. Well, E is with the mass. It's E M. And then I get the result for the two body. The same will happen at 2 p.m. as well. And this is very nice because up to 2 p.m., the Schwarzschild solution determines everything. Once you realize how this mass-dependent centers, and this keeps going. At 3 p.m. is where the first nu appears, so the one-cell force determines everything. And also up to 4 p.m. And then 5 p.m. you start getting the nu squares and so. And we noticed this when we did our first paper up to 2 p.m. And Thibault generalized it to all orders and said, look, then this happens everywhere, which is kind of straightforward generalization of what we did. And that's why also using self-force calculations could be very useful to learn through scattering about the scattering angle and through the connection to the bound case were observables for binary systems. And this, Thibault and Donato and Andrea have used this mass scaling very strongly to try to guess and constrain what the structure of the solution should be, and something that they call tutti frutti because they also use self-force data to try to input into this calculation. And maybe even Fabian talked about something similar in his talk, I forgot. I haven't told you yet how to go from here to bound, but let me just give you the flavor of how this continues, because this is just all there is. All there is keep going forward. How about 2 p.m.? 2 p.m. is exactly the same. I need to now go to the same guy I had before. Now I cannot say that the V's are used. I cannot say that the X is this. So I need to add what is called, what we call the iterations. What's the iteration? The iteration is the fact that now I had to put here a delta X and a delta V. But where did that come from? That came from the solution that I just erased. The P dot, this comes from the equation of motion. The equation of motion will tell me the leading order Lagrangian is eta VV. Again, this is the full V, but it's the leading eta. So there will be an equation for V dot mu that will have the interaction X plus d dt d dv and I just computed, for example, here my 1 p.m. interaction is right here. That's my action. So if I want to know the equation of motion, I take the derivative. I don't integrate. Then I have to stop because it's up to some time t. And now because I'm not integrating, I also need to keep this term. But all of this came from the 1 point particle exchange. So you could diagrammatically think about this, adding this iteration, as saying, well, but this came from the 1 p.m. action on the particle. And these are the type of diagrams that you can do if you quantize then the world line, degrees of freedom. But it's literally just adding the solution of the equation of motion. That's the first thing I need to do. I need to input these guys in the exact same calculation I did here, right? This will be the QED part of the calculation. Now I need to do delta x1, delta x2, and the dot, which will give me the delta v1 and delta v2, which are the dots of this. So this calculation is the same. I'll show you in a minute. It's usually, this is usually the annoying part of the calculation. The hard ones are here. Well, both are hard. And then I need to add this guy. But this is easy because this one, what integral do I get here? I get the usual one that I get in an RGR as well. The only difference is that it's 4-dimensional. Q is my transfer momentum, right? And L is the leftover Green's function loop integral. It will be the exact same thing in an RGR if you're doing the static case. M1, M2, M1, M2. You get the same integral. If you were doing the 1 PN Einstein-Liffe-Hoffman, you will land in an integral exactly like this, except that this one will be d3 L L square L minus Q square. And instead of doing a Fourier transform to impact parameter space and integrating and so on, here you have some potential, which will give you the 1 over r squared potential. Do I have the answer to this integral? Probably don't. Yes. So the answer to that integral in general, this is a master integral that appears everywhere. For those of you who have been doing this calculation, I'm sure if I put this in d dimension and I have some 2 alpha L squared beta, then this is a bunch of gamma functions. I'm not going to write it. But the important thing, 3? Yeah, exactly, 3, yeah. That we're going to also have here we're going to end up with something like this. And now the catch will be that the delta functions are going to do the same trick again as they did before and give you the d minus 2. Here in NRGR usually is 3. Sorry? Yes, in the Q integral that we do at the end. But there will be here also delta functions, because as we will see, we will localize everything when we're doing the tau integrals on the wall line. This wall line will also be tau, so it will also localize that guy. So at the end, you're going to end up with a purely static integral, also here. Because of the tau integral here, we localize it as well. Sorry? Well, but the only one that you care is that the LU will localize it. You have an extra L dot U that will localize the L. The Q is already localized, so this is localized. Yes. This becomes, the Q is 2, the L is 3. Is that what you're saying? Yes, yes. So this, in D dimension, it will become a 3-dimensional, like a potential integral, the same way that it becomes for us. And then the Fourier transform will give you the 1 over B. Yes. And this in D dimensions has all these gammas, and then there will be here, if it's x, is x to, what is it, square d over 2 minus alpha minus beta, I think, over 4 pi. This is standard. This, you can look it up. And this is, for example, all the things you need for the one loop in D dimension. That then you just 3. What matters here is that you're going to get the Q out. That then when you do the Fourier transform, will give you the 1 over B squared. That's ultimately what happens. And all it matters is at the end you get a factor of 1 over 8 or whatever it is. What I'm trying to tell you is that the same thing that happened in NRGR happens here. And the delta LUs will localize those things on the potential modes. And that's why there is no radiation yet. They are pure potential integrals. And then the last one is just the Fourier transform, which has these 2 deltas. Right? In other words, this force now is essentially the same force that you would do even if you add the radiation, this will naturally localize. Because these guys are touching the wall lines, and the wall lines have this delta LU, it will always make it potential. The only way you get something that is not like that is when you have a guy that doesn't touch the wall line. So this guy is at 3 p.m. He's the first guy that can radiate. This guy could be on show. If you touch the wall line, that delta, I did in order. Then, obviously, it would be an iteration, and then, this I can turn on. Because now this guy does not necessarily have a delta there. Although in this case, I don't remember now, this one might have a contribution too. Because even iterations of these guys have contribution later. Because this becomes like in QED, the radiation reaction Abraham-Dirac-Lorentz force that also radiates. So when you start iterating this guy, you also get integrals that will look like this, and it will be also radiative. Not if it's an unperturbed trajectory. In other words, if you don't get kicked, you don't radiate. The only way you radiate, this guy turns on if you get kicked, or if you couple to the binding. That happens in an RGR. This type of diagram with a potential is the tail. It's the interaction of the radiation with the binding. And the same is going to happen to us here. The difference is that I'm basically shrinking all the potential lines in an RGR. Here I have them all until the end. Okay. So let me tell you just what type of integrals we get. We get integrals like this, when there is another delta L, there's another delta U1, and there's the same with the mirror, there's L dot 2, so you get the three-dimensional integral there, and then the Fourier transform is the same as before, and then you get the 1 over V squared. The point is that you end up needing just the usual in RGR integral, which is the one that we have over here. And what else do you need? That's not the end of the story. You need one more integral, which is the one that comes from using the equations of motion that we need to plug here. So when we bring this down, this is when I took the derivative to get the impulse. But if this is my action, and I plug here the delta x, and I bring it down, then I do get the deltas back, but I bring down this guy, which itself will be an integral. So I'm going to get like a two-loop integral now, because this guy is going to have another integral. Now it's going to have up to t, but t is going to be integrated. So there will be another integral here on t that will give me another delta function. Sorry? Which method? No, the opposite. No, I think it was mostly angles. This is what Westphal calculated. In fact, I think nobody ever did a Hamiltonian out of this. Westphal in '85 computed the angle, not this way. He solved the Einstein's equations, I believe. I forgot my what. He got this number and the next one that I'm computing now. I don't know anybody who's ever done a Hamiltonian this way, to be honest. Did I write this in here? So what changes now respect to the, exactly. So I need the equation of motion. So I have the action, I take the derivative, and now what's going to happen is I have an acceleration times a force. The force, I'm tired, I will write, but you'll see what I mean and where it comes from, and then you will understand. Ask me later if you have a question. I was just going to write the structure, and then you'll see where it comes from. So the equation of motion, which is P dot that I had over here, P dot equal ds dx, which becomes the Lagrangian dx. Think about the Lagrangian of this guy, or for the particle 1, right? Which is integrated over this other guy. So this is integrated, but this is the action of this guy, so I take the derivative. When I take the derivative, I pick the time at which I take the derivative because I'm computing an acceleration. So I get an acceleration, x double dot equal some integral. But now, because I'm looking at the solution, which I plug the deflection, the solution for the deflection will be from the force. And for the force, what's going to happen is I'm going to have here some u. I'm going to put the unperturbed because I'm looking at the solution that already has the g in front. So for the equation of motion, I can treat now the unperturbed solution. I'm going to have a delta, right? But I have to solve for b dot. So when I solve b, I need to integrate. So I need to integrate that delta u tau that is going to end up in here up to some time t. And then what the problem I'm going to have is that that is not well defined, because I'm going to have an integral minus infinity to t e to the I k dot u to t prime dt prime. When I try to solve now the equation, which depends on tau up to a given time tau, because I'm trying to solve for the solution of v, so I integrate. I don't put the initial condition because I'm going to say that the perturbation vanishes, and I'm solving the equation for the perturbation, so at minus infinity I get nothing, so I get just the solution at t. We have this integral. Now this integral is not well defined because the boundary conditions. How do I make it converge? So I had to put a small I0. And if this is minus, I think this is plus, right? So when t goes to minus infinity, converges. And then the integral then will give me a k dot u 2 plus I0. Another way to see this is to put a step function. If you put a step function, and then you do the integral to infinity, if you don't want to do the I0, then you do the integral is up to t, so I have to integrate in tau up to t. And now the Fourier transform of this will give you, and this is like an omega if you want, the 1 omega plus I0 is exactly the same. That's all to say that I need to be careful with the boundary condition. And that's putting the correct retarded boundary conditions, if you want, that in minus infinity the field vanishes. That's just to say that when you solve the delta x, you're going to get these solutions that now are going to involve these linear propagators. So that means that, and that was also kind of pictorially why when you do things like this, I mean, you kind of have like a linear propagator there. It's also the reason why in amplitude, if I were, how do I do this with amplitudes? I need to get an angle. So I can put an action. From that action, I can construct, for example, an iconal phase that I take a derivative and I get an angle. So an amplitude that has like an iconal phase that is like a radial action, it knows about the angle. So the exponential of the action, right, is an amplitude, and the derivative of the action will give me the angle, roughly. How do I compute an amplitude? Well, I do the same. I send something in, I collect something out. There is also some momentum transfer, right? I look at large impact parameter. I look at the regime in which I can ignore that's angular momentum. I can ignore the corrections. But these guys now propagate. So you get diagrams also like this, where there is a propagation of that guy. But I'm going to go to the heavy mass limit. So the propagator, if I say P is mu plus something, will kill the big M, and then essentially you get the iconalized, which, by the way, is also how you localize the source in an RGR. Because that's essentially this combination that gives you a localized source at the end of the day. So it's a heavy mass limit of these propagators that localizes the sources that give us this type of propagators for us. So that's essentially also, some people are doing this heavy quark amplitude story, heavy black hole effective theory, I think it's called. But what this means now is that our integrals will involve also this k.u's. So essentially now what we have is going to have L.u1 plus I0, some power, then L1, then L2, U2. Then there will be quadratic propagators and da. Those will come from the diagrams themselves. They will give all these quadratic propagators, and from the iterations, I get the quadratic propagator, because each iteration will cost me a 1 over p squared anyway, as a force, plus the other guys that come from the iteration from the integral up to t. So that would bring me down this guy. Now I have to do tensor reduction, and because this integral now can depend on u. But the u direction, I don't quite need, because as I told you, the u direction that appears in delta p, I can bootstrap from the v direction using the conservation. So I can just look at the projection of these integrals in the v direction, and I know also that u dot v is equal to 0. And this is how we calculate. In the 2 p.m., for example, what's going to happen is that this one integral appears, and then there is another integral now that appears, which looks like this. So the other integral that we need is going to look like this. This is for one iteration. They have the other iteration from the other particle. It's the other way around. But then you see that you get the same as before, but now you get the extra guy from the equations of motion. You need to do the tensor reduction. There will be factors of gamma that then appear, but everything can be reduced into some scalar integrals. And this is the other one that appears precisely through this iteration that I explained here. And now you have to do this integral. And again, you have used so you have to deal with now with the u here, which is going to be you're careful, right? Because this is u2, so you can go to the frame of u2, but then this becomes the two components, or you can frame to the frame of u1, and then you have this other guy here. So you have to be slightly careful with the integral. You also have to be slightly careful because when you look at, this is the b direction, which is the one I want, but for example, if you want the u direction, then you also get a component that is this integral. And the reason is because I did a tensor decomposition, so then if I get the u direction and I dot with L, then there will be an L dot u that's going to kill one of these guys, and then I get only one. So if I look at the u direction, I also need an integral like this. Because remember, it's a momentum. So there will be a square and an L mu, and then what is in the u direction? So I dot with u to get the component of that u direction integral, and this L dot u kill this. So the A component of the u direction will be without the square. You see it or not? Yes or no? Maybe you're tired. I'm tired too. Anyway, the u direction costs you one fewer u. It's kind of obvious, right? Just in the tensor reduction. And now you see when you do this integrals, you're going to end up with an integral in which you have to close contours. And there are different procedures. We don't do it this way anymore, but if you work to close the contours, then you have to tell me what an integral like this is. And then you have to choose a prescription. When you close half one way, half the other way, these are the potential modes. How do you deal with the potential modes? This was the original idea of how the people in amplitudes also computed these integrals. Now we just solve them through differential equations. Well, this one is easy. But at higher orders, we solve them through differential equations, which is the idea that we can solve these integrals by seeing how they depend on gamma. But what is the bottom line? So what I want you to get out of this is that what is the structure? The structure is what I described. There is a delta P that comes from the action. The action I can compute exactly with generic trajectories. 1 p.m. action, 2 p.m. action, 3 p.m. That gives me equations of motion. I have to be careful with these linear propagators when I integrate up to t, and then I get a solution for delta x. I plug that back, and there will be an e to the I q dot tau, right? So when I solve this infinite to t, I get the linear propagator, and I also get tau. But then when I plug it back and I integrate in d tau to get the impulse, then this gives me a delta function, and this survives. So my integrals at the end is a bunch of quadratic propagators, a bunch of linear propagators, and I have to do them with a bunch of deltas, which are the opposite of these guys. Right? Obviously, it will be 0. And then at the end, I also have a Fourier transform. U1, U2, e to the I qb. And here, there are L's minus Q's and blah, blah, blah. An integral. That's all you have to do. How do we do them? Well, when we can do them at 2 p.m., we do them explicitly. This gives me the u direction. This gives me a correction in the v direction. Actually, if I don't remember correctly, I think that one doesn't even contribute because we don't have that cross box. But at the end of the day, the whole point of this is to compute integrals. Once you understood where this is coming from, it lands in an integral. How do we do it? Well, you reduce this into master integrals, which are irreducible integrals. And then you have a basis of integrals. And you take a derivative with respect to the parameter. The only parameter that we have is gamma. And then there is a matrix, which also depends on d dimensions of the master integrals. And then you try to solve this integral, these differential equations. And then you have a solution up to boundary conditions. And the boundary conditions you get by taking gamma to 1. And this is the Pn limit of small velocities. So we reduce this type of integrals to the Pn version of the integrals. And that here is where we use the method of regions. And let's do the following, because now I'm getting tired. Next time, I will just do 1 hour. I'll show you one example of how one of these integrals is done, and then I'll show you how we map the chi to observables for bound, which is the end of the story. How do we get now from an impulse to an angle, and now to bound, which is the part that I haven't told you yet. All of this is to get this impulse, right? Now I haven't told you how we use this information to get the bound case. That I can do next time. Because I realized that this is way too much information now. And I will have to at least give you one example this example gives you in detail. Try to do the 2 p.m. calculation. It's in our paper. And see if you can follow the integration problem. The most interesting aspect is like, how do you systematize this, right? And the systematization is interesting because then you can try to solve these differential equations that will give you a general solution to this integral with some boundary conditions. And the boundary condition is where this method of regions enter. Why? Because you get integrals, for example, you start with integrals, a 2 loop that look like this. That you remember there's k-squares, and then those k-squares can kill the propagator. So some of the masters associated with this type of diagrams could be this guy. So essentially, it's 3 momenta, L square, L1, L2 square, L1 plus L2 minus Q square, and then say delta L, the deltas that appear in the integral, and then the Fourier transform that appears later. And then you have this type of integrals you need to solve. Sometimes we use reverse unitarity. For example, you can rewrite these deltas as 1 plus I0 minus I0. and that reintroduces these linear propagators. So when you do amplitudes, you often get this type of guys. We get the deltas already because we don't have the crosses, the box and cross box F, because the propagators of the wall line are localized. But then we get the same type of integrals that they get in the amplitude business, and you have to do an integral like this. And then you have to look in the regions, and there are different regions because now this guy can be on shell. How do NRGR do this calculation? Well, NRGR doesn't do this integral. NRGR computes the potential, the pure potential, which we can also do, the pure potential part, will be exactly the same integral that you get in NRGR. NRGR will also cancel the propagators. You also end up with a pure potential integral like this, which you know the answer for. But you also have a region when this guy is on shell. But what does NRGR do? NRGR matches into this theory of Q's, and that's this guy. Here we cannot do it reversely. We look at the regions, and there will be a region where this line can go on shell. And then you look at the regions of the integral, how the momentum, you call this K. And then you have the potential region, but you also got the K in which you rescale the K by V in both regions because it can go like V. So this is a radiation guy. It's VV now, space and time. And then you look at now when you resolve the delta function, and you write this as K and so on, you end up with an integral in which the part in which this propagator can go on shell will factorize, and you do that integral first. And it will depend on the potential, the L that will still be flying around, and therefore you're going to have, because when you solve the delta function here, the K will mix with the L, and then you have an integral here that will look a lot like a K squared minus L dot N squared. The L, when you solve the delta function in the U2, remember there is a 1, 1, so there will be like an LC component. This is the one that looks like an omega. So you match this, you first do this, where the potential you do last. So you first do this integral, where this is a K L dot N type omega frequency. And then you get an L integral that you do last. But you end up with integrals that have these L dot N's in them, which are non-trivial to calculate. But then once you have that, in that region, you run to all orders in gamma through the differential equations, you get the full solution. So there is a way to map what we do in NRGR to what we do here in the boundary conditions of this integral. And that's the whole story. You do it at one loop, you do it at two loop. You do it at two loop, you start seeing these radiation modes. So in the conservative sector, you're not going to see this. This is going to be complex. So you're going to throw it away. And the 3PM calculation that was done first for the angle is purely potential. And that's when you start saying this R sinh of gamma, which is pure potential. So at 2 p.m., you still have the phi gamma squared minus 1, the chi 2 p.m. over gamma. Again, the nu dependence, everything here, which is very nice. No nu here. But then at 3 p.m., then you get the R sinh, which becomes this log of x, where the x is a function of gamma. Gamma is x squared, 2s squared. Okay, I don't remember exactly the parameterization. It's x squared. Okay, I forgot how this, because 0 and 1. Anyway, not important. It's a R sinh gamma squared minus 1, which becomes the log of x. It's a gamma dependence of a more complicated function that resumes all the velocity. It's 2 squared. Shit. I forgot the 2 squared plus 1. Anyway, it's the famous R sinh. But now you start seeing the nu dependence. And that is nice, because now is when you start seeing departures from the fact that the theory is uniquely determined by the test body. But this 3 p.m., this integral is just a complicated H integral, pure potential. It's really the pure potential part of this, which these integrals are a little bit more complicated because they have these delta functions. But it's pure potential. If you want to include the radiation, you have to do the in calculation. Then this boundary condition here matters, whether you have the I0 here or the I0 inside, and then the integral that was complex becomes real. And then you do get corrections now from the radiation that don't have R-singe. They are polynomial in the radiation, but the potential part is the part that usually is the more complicated, because at 4 p.m., you get the K and E elliptic integrals from the potential part of these boundary conditions. And then you also get dilogarithms, like Li2 and so on. Complicated functions of mostly the potential part is the part that is usually the complicated part. The radiation, also in NRGR, the radiation integrals are usually easier in terms of the structure of the integral as well. The potentials are usually the hard ones. And that also comes now from having diagrams like this. And now comes something very interesting, which is completely new. Everything seems to decouple. All the conservative part up to here becomes just pure potentials. And then the dissipative part comes once you add the fact that you need to work with retarded propagators, that basically, instead of giving you, there's a crucial sign. There's the I pi in Feynman, and there is the I pi sine of omega in retardeds, and that makes it real. And that will give you the radiation reaction part. At 4 p.m., you start getting these integrals in which now you have 3 loops. This guy can be on shell. Now you have 2 integrals like this. And that is essentially matching into a diagram like this in NRGR. Like in NRGR, there is a tail. And therefore, we're going to see also a real part of the Feynman calculation, which is conservative, coming out of the tail. So there will be a radiative contribution to the integrals, which is conservative, starting at 4 p.m., which gives me the log of V. And where that comes from is because, remember, I rescale in B, so every potential mode will come rescaled with the measure in D dimensions as V to the minus 2 epsilon. It will cost me every potential mode when I do rescaling of the boundary condition, it will cost me a V to the 2 epsilon. There will be a pole from the tail region. As we know in NRGR, there will be a pole in the potentials. The pole will cancel, but the log of V will survive, and that will give me the log of V. So there's a beautiful structure of integration that mostly potentials will give you all these resum functions of the velocity. Then there is the radiation modes that gives you the logarithms from tails. This logarithm, by the way, if you try to match to a Hamiltonian, is what gives you the time non-locality, which is the part that is complicated. Not the log itself, the log is universal, but this log comes with constants, and those constants depend on the trajectory. You do this systematically, pop, 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 and then you get everything. You get all the contributions that come from potential, all the contributions that come from radiations, one radiation guide that's usually just the leading radiation reaction forces, 2 radiation guides that includes radiation reaction squared, but also tails, and so on and so forth. Get a complicated integral, you solve it through differential equations, and then the boundary conditions are matching into the NRGR type of integrals in which the method of regions tells you how to rescale your momenta to compute the boundary condition, and that's essentially what contributes to all these integrals. That's basically the story. And there are many ways to systematize this. There are many ways to set up the beginning. We set up the beginning in this classical effective theory. There is the amplitude story, in which you do something similar. There is the wall line QFT, in which you quantize the wall line. Everything boils down to the same type of thing, which is doing these integrals. And so far, I'm doing the scattering. I'm mostly concentrated in conservative, but if we do the retarded boundary conditions, we get the dissipative part as well. Then the delta P's are not going to say delta P, delta P2 are going to be equal. Then there will be a total delta P radiated. That's the total energy. And now the question is, and I'll show you this next time, what do I do with this? I get an angle which has all these features. What do I do with this information if I want to describe bound orbits? That's the part that I haven't told you yet. Okay? Yes, I think in terms of how the structure of this works, with some Obviously, you have to sit down and do the calculations to see where the things come from, but basically the flavor of understanding these are gravitational interactions, these are the wall length propagators, and all of this comes from the tau integrals at the end of the day. Then you understand what more or less the structure of this is, and then it's computing integrals. We can spend months we wrote a whole book on how to do these integrals. But the whole point at some point is that we need help in understanding how to solve these integrals. These differential equations are very nice because it's only one scale in the problem. One scale in the problem means I can try to solve this. There are ways to solve this when this is canonical, which means if it's a logarithms and dilogarithms and polylogarithms, when the elliptics start to enter, then those tools fail. But we were able, Christoph Lapa had some ideas on how to solve this when there are elliptics, which is non-trivial. And then together with Gregor Kalin and Chen-Wen Liu, we did all these boundary conditions to basically solve the full problem, for example, at 4 p.m. And that's how we got, for example, the full scattering angle, including all the conservatives and the dissipative parts, which was boiling down to compute all this integrals. And now you have to ask me, well, what do I do with this? And that comes next, okay? All right. Do you have any question? Yeah, as I'm talking, I'm realizing there's way too much information for such a compact amount of time. But you get the flavor, which is mostly what this is about. He has a question, right? No? I thought Alan was going to ask a question. No? Now you're forced to ask a question.
So the way the UCLA group computed first was they quantized the word line.
No, they didn't have a word line. They computed an amplitude. So they did an amplitude. So say 2 to 2. And then you compute the scattering amplitude.
As a function of the momenta.
Well, at the end of the day, you get the P1, P2, the function of gamma. I mean, the momenta, the P1, P2, P3, P4, all of those. Yes, exactly. And then you can match into an effective theory in which you have like a Born-type potential. And that's what you use then to say, okay, this is my potential associated with that amplitude. And then you Fourier transform, and then you get a form in R. And that's the potential that will give you, for example, an angle or whatever that you can calculate. So it's...
Okay. The scatter plane waves.
Sorry?
The scatter plane waves.
Well, you match the full, how they build this through many tools, and then you match into what you will do if you have quantum mechanics. And then you do just the classical part of it, and then you extract from there a potential. The point is that you need to add all the iterations, the Born iterations and things like that, which is the non-trivial part. We show actually from here that it's very nice because there's a classical limit of the amplitude that if you then go ahead and Fourier transform, you get the so-called impetus formula because directly the amplitude will give you the coefficients of the p-square. In some representation, in some basis, the amplitude is the momentum. Then they found another basis in which the amplitude is the radial action because it's basically the integral of the momentum will be the radial action, which is basically like an exponential that gives you an amplitude. So we realized, they realized themselves that we basically studied to all orders that the amplitude was giving you the momentum, that you didn't have to do this matching into the Hamiltonian. But then later they realized that they could change the basis and map instead of p squared the radial action. And they used this because the derivative of this with respect to J is the angle. So essentially they compute this by matching. Basically it's like the Born iterations, but the Born iteration becomes trivial with the subtractions. So they found a way to trivialize the subtractions by finding a different basis that goes directly to the radial action. But it all goes to an amplitude that then you can match into a classical theory in which you extract some information. In this case, it's nice because they don't go through a potential, they go straight to the radial action. Before, we also did not go to the potential, we went to the p-square. And the p-square, by the way, is what I told you earlier. It's very nice. Imagine I'm not doing anything with bound, but I get an angle. For that angle, I get the p-square. If I know the p-square, now I compute the radial action. And now from here, I get an angle. And this angle was up to 4 p.m., say that we have it. Then this goes to G4. Then I put it here. But when I do the integral here, I get all orders in G. So now this is a total angle that gets all orders in G. So I can use now this as a resum version of this through this procedure.
So the p square is the function of the energy.
Who is p squared? The thing is that this I construct such that this matches this up to G4, but includes all the other terms.
No, but the p square, what you call p square?
H is a function of R p squared. If I invert this, I get p squared as a function of R and E, or gamma. That's the p squared. It's the momentum, what I call the impetus formula, meaning how the momentum changes as the distance for a fixed energy as the gas gets, exactly. And that will give you what the radial action is if you integrate it, and from there you get the angle.
Okay. Everybody's tired? Okay. We thank Rafael.
Thank you.